All right, so far we have actually been doing differentiation with y's and x's, but we've only had one y, and it has been our function. Y equals something, okay? So we really are trying to get to the point where we can now have x's and y's within our function, and it's called implicit differentiation. So far we have had it in explicit form. So like this would be considered implicit form, where you have your x and y's on the same side. Explicit form is when you get your y by itself and have the x on the other side, and then you can take the derivative, right? But there are times when you cannot get the y by itself to explicitly define the function, and you need to do implicit differentiation, all right? And so you basically derive each piece individually like you would, and then you're gonna simplify. So for example, we've been doing derivative. Dydx is a form to write the derivative, and we've been doing it with x's in our function. So these variables agree. What I'm deriving with respect to agrees with my variables that I'm deriving them from. Here, if I took the derivative, these variables do not agree. That means I have to use an implicit type of differentiation. All right, I have to use an implicit type of differentiation. And so when they agree, I am just going to do my rule. Well, the derivative of x cubed is just 3x squared. That is simple. All right. But if they disagree, I have to account for that. This is going to be 3y squared, but then I have to tell them that I am deriving the y with respect to x, and I have to put this little dy dx here. Now here's what we've been doing. Dy dx represents your derivative of y. So we've been doing something like this. And technically we have been deriving. The derivative of y is just 1 dy dx. And then we have 12x cubed plus 2. All right. So technically we've been finding dy dx. It's just already been by itself, and we haven't had to worry about it. Now we're going to do some where it's not by itself, and we have to get it by itself to actually solve the problem. All right. And so if you look at C here, they want the derivative of this guy. All right. So basically we would derive this exactly the same. We would say, well, the derivative of x is 1, but the variables match for that. So we can just say 1. The derivative of y, 3y, is just 3, but those variables do not match what I'm deriving, so I have to account for it. 3, and I took a derivative of a y with respect to x, and so I have to plug that in there. For this one, I have to use product rule, because I am multiplying an x and a y squared. The derivative of x is just 1. The derivative of y squared is going to be 2y, and the variables disagree. So dy dx, because these variables disagree. So I have to put that little dy dx in there because I derived a y value, and I have to tell them that I am deriving it with respect to x. All right? Well, what does that do when I do the product rule? Well, the derivative of the first one, that's just 1, times the second. I did not derive the second yet. Then I'm going to say plus the first times the derivative of the second. Well, the derivative of the second is 2y, and I actually did something with the y, so I have to put that little guy there. So anytime your variables disagree with what you're deriving with respect to, you have to tell them you derived it with respect to that variable, okay? Guidelines for implicit differentiation. Differentiate both sides of the equation with respect to x. Collect all your dy dx's on one side of the equation and move everything else to the other side. Factor out your dy dx and divide over so that you get the dy dx completely by itself. And then you have the derivative of the function. And it will have x's and y's in it, typically. All right? But you have to make sure you have moved all your dy dx's to one side and everything else that doesn't have it in the other side before you do this. We have this function here. I have y's and x's. I cannot get this explicit right now. I can't solve for y. There's no way to do that, right? You can see that I can't solve for y. So what I can do then is I can implicitly differentiate it. So I'm going to differentiate each piece. I am differentiating with respect to x. So anytime I derive something other than an x, I need to put my dy dx there. So I am going to take the derivative of y cubed. That is just 3y squared dy dx. I have to take my derivative of y squared. That is 2y dy dx. I have to take my derivative of negative 5y. That's negative 5 dy dx. And I have to take my derivative of negative x squared, which is negative 2x, but those variables agree. I don't need to put anything with it. I also have to take my derivative over here, but what's the derivative of a constant? It's just 0. All right? So now I need all of my dy dx's on the left-hand side and everything that doesn't have a dy dx on the right-hand side. So I need to move this 2x over first because he does not have a dy dx. So I'm going to move him over. And over here, I'm going to now, because everything has a dy dx, I can factor it out, okay? So I can pull the dy dx out, and I am left with 3y squared plus 2y minus 5, and that equals that 2x over there. Now my goal is to solve for dy dx, so now I can just divide by the group. I can divide by this entire group on both sides, and I'm going to get that my derivative, dy dx, the derivative of y with respect to x, is going to be 2x divided by 3y squared plus 2y minus 5. And that is my derivative. So find the slope of the graph implicitly. So they want the slope of the tangent line to the graph, all right? Slope of the tangent line to the graph. And they give it specifically at the point, which I didn't copy here, but specifically at the point square root of 2, negative 1 over square root of 2. Let's pick an uglier point than that. All right, square root of 2, negative 1 over square root of 2. So they want the slope of the tangent line at that specific point. Well, this is going to be implicit differentiation. So I'm going to derive the x squared, 2x. I'm going to derive the 4y squared, 8y, equals 0. Subtract that over, so I get 8. Oh, and I do have to do this guy, dy dx. Subtract that over, I have 8y dy dx equals negative 2x. Divide dy dx is going to equal negative 2x over 8y reduces to negative x over 4y. I am not done. They want the slope of the tangent line. You'll notice that I have an x and a y. So when you have explicit differentiation, you really only have to plug in the x because your y is gone. It was by itself already. But when you have implicit differentiation, you actually have to plug in your x and your y to get the slope of the tangent line. All right, so I need to plug in both of these. So I'm going to have negative square root of 2 over 4 times negative 1 over square root of 2. Keep, change, flip. So you have negative square root of 2. Actually, it's negative over negative, so you can just ignore the negatives, actually. So you have square root of 2 times, this is going to be square root of 2 over 4. That gives you 2 over 4, which gives you 1/2. Your slope of your tangent line is 1. So chain rule here, because of this, I have to do 2 times that 3, which is 6. X squared plus y squared to the first power. And then the derivative of the inside is going to be 2x plus 2y. I derived a y, so I have to do dy dx there. All right. On the right-hand side, I have to do the product rule. The derivative of the first is just 100 times the second, which is y, plus the first, 100x, times derivative of the second, which is just 1 dy dx. All right. So at this point, I need to start really distributing and getting that dy dx on the left-hand side. The only way I can get it on the left-hand side is really to get those things out of parentheses, you know. So I'm going to distribute. I have 6x squared plus 6y squared, right? That's being multiplied by 2x plus 2y dy dx equals 100y plus 100x dy dx. All right. So far, so good. Foil this guy. So we're going to say 6 times 2, that's 12, and my x's are cubed. 6x and 2y, that's going to be 12x squared y dy dx. Here, I'm going to get...
Wait, isn't it 12x squared 2y?
I multiplied the 6 and the 2 to make it a 12. Then I'm going to multiply the 6y squared and the 2x. So it's going to be 12xy squared. Then these two, that's going to be 12y cubed dy dx. And over here, it's as simple as it gets already. All right. So what I want to do is I want to get all my dy dx's over on the left-hand side and all of my non-dy dx's, so to speak, on the right-hand side. All right, so the ones I'm going to keep on this side, I'm going to keep this, and I'm going to keep this. So I'm going to move the other ones over, and then I'm going to move this over. So you end up with like 12x squared y dy dx plus 12y cubed dy dx, and then I'm going to move this guy over, minus 100x dy dx, right? And then on the other side, I leave him alone, and I move these over, minus the 12x cubed, minus the 12xy squared, right? Does that make sense?
Oh, yeah.
I mean, this is just algebra, moving one side, moving to the other. Right, we're solving for dy dx. So now at this point, I can actually factor it out. It's in every one of those guys, right? So I can pull that dy dx out. And I'm going to get that group of these guys here, right? Equals this guy over here. And I can divide by the group. So I get the 12x squared y plus the 12y cubed minus the 100x, right? And over here, I have this big old guy. I'm not going to rewrite it, okay? But you see, you've just factored out. Once you factor, you can divide by the whole group. So my dy dx is going to look like this. It's going to be this group, 100y minus 12x cubed minus 12xy squared, all over this group, what was left over, the 12x squared y plus the 12y cubed minus the 100x. So it doesn't matter that it's complicated looking. You're doing basic algebra. You are distributing, you're foiling, you're factoring out. That's all you're doing. Your goal is to get dy dx by itself. For all implicit differentiation, your goal is to get dy dx by itself. All right? It doesn't matter that it's huge or anything else. It doesn't matter. Okay. And once you do that, you can just plug it in. So if they ask for the slope, you're going to have to plug in your x's and y's. If they ask for the derivative, you're done, right? So it just depends on what they're asking for to find out if you can or cannot reduce it, do it. Now, like if they want a derivative, I would actually reduce this. Can you see something can go into all of those? What can go into every single one of those? None of your variables match, but for your numbers, a 4, right? So if I were doing the derivative, and even if I were plugging in, just for sake of not having ginormous numbers, you can reduce all of these by 4. So you see you have 25y minus 3x cubed minus 3xy squared over 3x squared y plus 3y squared minus 25x. So you can reduce it.
3y cubed.
Was it cubed? Oh yeah, that's a cubed. You can reduce it if something comes out of every single piece of it. You can reduce it, right? And then at that point, you would just plug these into your x's and y's and get a slope. And I think they get like 13/9, something crazy, when they plug it in. But it's a matter of deriving each piece, using your chain rule, using your product rule. Anytime you take the derivative of a y, not where you have a y. Like up here, I have a y. I didn't put dy dx because I didn't actually take the derivative of it yet. But I did put the dy dx here because I took the derivative at that point. So you're going to take each piece and derive each piece, whatever method you need to derive it. Move all your dy dx's over to the left. Move everything that doesn't have a dy dx over to the right. At that point, you'll be able to factor that guy out and divide by a group. And then you're really done unless you can reduce it or unless they're saying, hey, give me the slope and you have to plug something in. So don't let the ginormous numbers scare you. It's the same process over and over that they're doing. Same exact process. They're asking kind of an interesting question here. And I just actually want to show you the fact that you would have to use implicit differentiation here. Because technically, you have the sine of y equals x. So this is actually kind of the fact that you are deriving a y, even though it's within the sine function. So if I were to take the derivative of this, it would be the cosine of y, right? But I'm deriving a y. So the cosine of y, technically times the derivative inside, which is 1, but I have a dy dx here. And I have to take the derivative of the other side. Don't forget you have to take the derivative of the x, which is a 1, right? And then to get dy dx by itself, I have to do what? Divide by cosine. So dy dx actually equals 1 over the cosine of y. I could probably simplify that even. What's 1 over cosine? Secant. It's secant, right? So it's the secant of y. All right, secant of y. They actually want to know where that is differentiable. And so you have to think about where is the secant undefined. The secant's undefined anytime the denominator, anytime your cosine is 0, right? And so it would be defined from negative pi over 2, right? Because that's where it is 0 on the bottom. You're good really anywhere up until where it's the top. So that's where it would be defined, wherever it's not 0 because you have a denominator there. But the derivative is what I want you to pay attention to. If you're taking a trig function of y, you have to throw in your dy dx there, all right, if it's with respect to x.